Welcome to this primer on functions. We will continue our discussion from last time. In this lecture, we'll learn about injective and surjective functions. And since we didn't do much the last time, there is not much prerequisite, but let me recall anyway. So a function from a set A to a set B, whose name is little f, you could choose any name, is an assignment of exactly one element of B to each element of A. So if you take an element of A, the function eats it and outputs some element of B, but only one element of B. And that is written as f of A. So this is how we read it. Maybe I didn't say it the last time, but this is read as f of A. Okay. So the domain of the function is the set of all the inputs. The target is what we write here. So it is not necessary that every point in the target has a counterpart whose output is that element. No, that is not necessary. But everything in the domain, meaning the input set, has to have some output. Okay, so image given any subset of the domain the image the f image of S is written this way, fs, and is nothing but all the outputs that you get as you vary over S. So that's the notion of image. And similarly, we have pre-image. So this time, if you have a subset of the target, then the pre-image or pre-image with respect to F of this set is all those points in the domain which map in the set T. And this may very well be empty. This could be an empty set. Okay, so let's continue. Injective functions. So suppose we have a map from a set X to a set Y. Then we say that f is injective if fx equals fx prime implies x equals x equals x prime. So what it's trying to say is that two different inputs cannot give the same output. That's what this says. So whenever you see that two inputs give the same output, actually the two inputs must be same. So here is a pictorial way to look at it. Here is what is happening is if you pick two different inputs, you will see two different outputs. All right. The function may leave some of the things in the target hungry. That's fine, but every input has to have some output. When you say the function is injective, you impose an extra condition that two different inputs cannot lead to the same output as evident in this picture. This is how one can succinctly express the same idea. Okay, so an injective function is also called a one-to-one function, but I will refrain from using this terminology. I like this. So inject, it's I think coming from the word inject, and you're injecting the set X in the set Y. So information is not lost in some sense. It's just that they get different names. Under F, they may get different names, but all of them have preserved their identities. They do not coalesce when you apply F. All right. Let's see some examples. So here we have a function from z to z, which takes an integer n and outputs n plus 1. So is it injective? Let's see. So to check injectivity, let's say f of n1 equals f of n2. Then n1 plus 1 equals n2 plus 1, which implies n1 equals n2, and hence indeed f is injective, because that's what injectivity means, right? And it was anyway clear. I mean, you cannot get two different n's to give the same output if you're just adding one to your input. So that's a simple example. The next example is, suppose we have the function n to z, naturals to integers, defined in this fashion. then is it injective? It is indeed injective because suppose f of n1 equals f of n2, then n1 square equals n2 square. Therefore, n1 square minus n2 square is 0. Therefore, n1 minus n2 times n1 plus n2 is 0. But since n1 and n2 are natural numbers, this thing cannot be 0. This is at least 2, in fact, and therefore this must be 0. So this means n1 minus n2 must be 0, and hence n1 equals n2. So whenever f of n1 is f of n2, we get n1 equals n2, and therefore the function f is injective. However, if we take the function defined from z to z, which takes n and it spits out the perfect square, spits out the square of the input, then this is not injective simply because f of minus 1 is equal to f of 1. So this is not an injective function. So let me write it down. This is injective. This is injective. This is not injective. Okay, so I hope the idea is clear. This is a very, very simple concept and also very important. Surjective functions. So this time we again fix a function from a set x to a set y. We say f is surjective if basically nothing in the target is hungry. So if for all things in the target there exists something in the domain such that f of x equals y. That's the definition, or alternately one could write f of x is equal to y. It's the same statement because what is this? This is the image of this guy under f, which is f x x in x, and saying that nothing here is hungry means that everything looks like this, and therefore this is the entire set y. So this is a succinct way to express surjectivity, but I have expanded it out here. So once again, for each element in the target, there is something in the domain which maps to it, right? So that's a surjective function, and a surjective function is also called an onto function. But again, I will refrain from using this. This is what I will use. Okay, let's see some examples. So this time again we have the same 3 examples, I think, or no, a little bit different. So the first one is just add 1 to your input, and is it surjective? So to show surjectivity, of course, I'm sure you can see this is surjective. This is basically just translating all the integers by 1, so it has to be surjective, but a formal proof is here. So let m and z be arbitrary, then f of m minus 1 equals m, and this is it. That's the proof. So you pick an arbitrary point in the target and you show that there is something in the domain which maps to it, and that's it. That proves surjectivity. All right, so this is surjective. Okay, the other one. So this time you are going from the naturals to integers, and this is the map is just add 1 to the input. Is it surjective? It is not, because if f of n equals 0, so okay, to be completely formal, assume it is surjective. Assume f is surjective, then there exists something in the domain such that its image is 0, because 0 is in the target, which implies n plus 1 is 0, which implies n equals minus 1, but minus 1 is not in the domain, right? Minus 1 is not in the set of natural numbers, so this is not surjective. That's a contradiction that we just arrived at, and hence the function f is not surjective. What about this guy? It's sending an input to the square of it. Is it surjective? It is not surjective, and I leave this as an exercise. The point is that the outputs are all only perfect squares. In fact, only positive. In particular, all the output are non-negative. And this contains negative numbers. So that is one way to argue that this is a non-surjective function. Okay, so this is it for this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.